In this video, we're going to examine what the entropy of a reaction is, as well as build upon some predictive tools we can use for describing what happens to chemical reactions and its entropy when we don't necessarily have values for it. Now, officially, the definition of entropy is equal to the change in heat during the course of a chemical reaction for a reversible process, meaning that we're using the maximum amount of heat that the reaction should give off or consumed, divided by the temperature the reaction's done at in Kelvin. Now, rather than keeping track of heats of reversible reactions, what we can do is we can actually look at the change in entropy of a reaction by comparing the sum of the entropy of the product molecules minus the sum of the entropy of the reactant molecules. So let's just consider a simple phase change here. What can we gather from this? Well, before doing any sort of calculation, we can see that going from water in the form of ice to liquid would result in an increase in entropy just because that the molecules are spreading out during the course of the ice melting. And so in the liquid state, we have some mobility, and therefore we have increased the entropy of the water. Likewise, when we boil the water and release water vapor, the water molecules have a much greater entropy than they did before in both the liquid or solid phase. And so the gas phase has a much higher entropy compared to the liquid or the gas. However, the first thing you should be able to take home from this message is that solids of a molecule always have the lowest entropy, and the gases of that molecule always have the highest entropy. And this, again, is due to the spreading out or the more chaotic nature of the phases. Likewise, we can look at the change in entropy from going from liquid to gas, that is, from boiling water. Over on the right-hand side, we have a table involving several different molecules in different phases, and we can see here that liquid water has an entropy of 69.9 joules per Kelvin mole, and that gaseous water, or water vapor, has an entropy of 188.7 joules per mole Kelvin. Well, to determine the actual change in entropy, we can take the sum of the products minus the sum of the reactant entropies. So for water going from liquid to gas, we can take the entropy of each molecule and subtract it. That is, subtract the product side from the reactant side. So we have 188.7 minus 69.9, giving us a change in entropy of 118 joules per mole Kelvin. So the entropy increases, meaning that the water molecules are spreading out during the course of this process. So what can we take home from this example? Well, if we look at the table here, first thing you'll probably notice is that there's not a single negative entropy value for a molecule. Not for a reaction, but for a molecule. Molecules must always have an entropy greater than or equal to 0. There's no such thing as a negative entropy for a molecule. Molecules in the solid phase have a lower entropy compared to that of the liquid or gas phase. As mass increases, so too does the entropy. Comparing bromine gas versus iodine gas, we can see that there is a difference in the entropy of those molecules. Another thing that causes entropy to increase is the number of bonds that the molecule has. You can see between methane, CH4, and ethane, C2H6, the entropy increases, one, because the mass goes up, and two, because the number of bonds has increased. Now let's shift gears and talk about some observations we have about entropies of reactions. A reaction can have an entropy that is positive or negative. If the entropy change is greater than 0, the reaction is creating disorder, or probably a better way of putting this is that things are spreading out. When entropy is less than 0, the reaction is producing something that is more ordered in nature compared to where it started with. So a positive entropy means that we can have more product molecules than reactant molecules. Likewise, a negative entropy for reaction means we have more reactant molecules than product molecules. Reactions, unlike molecules, can have positive or negative entropies. When delta S of a reaction is greater than 0, that means that the reaction is creating disorder or things are spreading out. Likewise, when the entropy of a reaction is less than 0, that means things are becoming more organized or less chaotic. Another note about entropy is that when the entropy of a reaction is positive, it means that there could be more product molecules than reactant molecules when we end. Likewise, if the entropy of a reaction is going to be negative, then for reactions which have more reactant molecules than product molecules, that is, there's a decrease in the number of ending molecules compared to when we start. Both of these are factors that go into determining entropies of reactions. Some other notes about entropy deal with gases. If we increase the volume of a gas, there are more positions for the molecules to occupy, thus resulting in more microstates and an increase in entropy. Likewise, if we increase the temperature, whether it's a solid, liquid, or gas, then the average kinetic energy increases, and the result is a greater distribution of molecular speeds, and therefore more possible microstates. And finally, if there's no net change in the total number of molecules during the course of a reaction, then entropy may be positive or negative, but delta S reaction will be small. If a constant number of moles of a substance expands at constant temperature into a large volume, then delta S will be greater than 0. So let's take a look and apply what we know about entropy and entropies of reactions to the following equation. Would you predict entropy of this would be positive or negative? That is, 2 zinc plus oxygen goes to 2 zinc oxides. Well, what do we see? We see a solid and a gas goes to a solid. We see we have 3 molecules on the left and 2 molecules on the right. So delta S here is going to be negative. There's a decrease in entropy, primarily from the fact that we went from 3 molecules to 2. But not only that, another benefit of looking at this reaction is we can see we went from a solid and a gas to just a solid. And we know solids have the lowest entropy state of the 3 phases. So those are the 2 reasons why we would predict delta S for this reaction would be negative. Now, is it possible for us to have an entropy of a molecule for 0, so no longer talking about reactions? Well, the answer is yes, it is possible. What's the requirement? Well, we can only have 1 microstate. Natural log of 1 is 0, so the entropy of 0 means that you only have 1 microstate. How can you have 1 microstate? Well, you can't have any kinetic energy, therefore we must be talking about a solid. This solid can only have 1 type of interaction in it, therefore the solid must be pure. All interactions must be equal to each other, that is, the bond length between all atoms must be the same. Therefore, the solid must be in a perfect crystalline structure. And finally, because we're in a solid with no kinetic energy, the crystal must have a temperature of 0 Kelvin. When you have these conditions, we say we have the third law of thermodynamics, which states that the entropy of a pure, perfect crystalline solid at 0 Kelvin is 0. So we've got the first law of thermodynamics, which says energy is neither created nor destroyed, and we have the third law of thermodynamics, which states that the entropy of a pure, perfect crystalline solid is 0. But wait, do you know what the second law of thermodynamics is? Well, we haven't talked about it yet, so let's chat about it for just a little bit. The second law of thermodynamics deals with the entropy change of the universe. The entropy change of the universe must be positive for any spontaneous process. Thus, the universe must become more spread out or more disorganized for a reaction to be spontaneous. That is, delta S universe must become greater than 0.